We now understand what are vectors and we can do some operations with them. We can add and subtract them and we can multiply them by scalars, but we also want to be able to multiply two vectors together. There are actually two ways that we can multiply two vectors. And the first kind of multiplication will give us something called the dot product. Let's learn how to form this operation. The dot product is fairly intuitive. If we have some vectors, a with component a1, a2 and a3, another vector with components b1, b2 and b3, then its dot product will be denoted this way as a dot b. This will equal to a1 b1 plus a2 b2 plus a3 b3. It is very important to note that this is a scalar product. The dot product doesn't give us another vector. It takes two vectors as an input and gives us one number as an output. For example, if we have a is 2, 4 and b is 1 minus 3, then a dot b is equal to 2 times 1 plus 4 times negative 3, or 2 minus 12, which gives us negative 10. Because the dot product involves a simple multiplication, its very intuitive properties, a dot b equals b dot a, because it doesn't matter what the order in which numbers are multiplied. The disruptive property also holds, and a dot the sum of b and c, or a dot the vector. That results from adding b and c. It's the same as a dot b plus a dot c. A scalar times a vector involved in a dot product is the same way as a scalar multiplied by a dot product, or the other combination of scalar and vectors involved in the same dot product. A dot a is simply the length of a, quantity squared. The 0 vector dot a is just number 0 because we are just multiplying each component of a by each other component of the 0 vector, which are all zeros, and then by adding all of the zeros we get 0. The dot product also crops up in an interesting theorem, which says that for two vectors a and b, a dot b is equal to the length of a times the length of b times the cosine of the angle between them. This means that if we want to calculate the angle between two vectors, we can simply bring up these vectors' length to other side of the equation, and we can get cosine theta as being equal to a dot b divided by the product of the vector length. This is one of the reasons that dot product is very useful, as it gives us a great way to calculate angles without doing any trigonometry. Let's give it a try. What is the angle between vector a with components 2, 2, minus 1, and vector b with components 5, minus 3, 2? Well, first let's find the length of each vector. For a, that's 2 squared plus 2 squared plus negative 1 squared, all under the square root. We simplify to get 9 and then take the square root to get 3. For b, we first 5 squared plus negative 3 squared plus 2 squared under the square root. We simplify to get 38, and we can just leave it as root 38. Now let's perform the dot product. By multiplying the corresponding components, we can get 2 times 5 plus 2 times negative 3 plus negative 1 times 2. That's 10 minus 6 minus 2, or 2. So plugging everything in, we get 2 on the top and then 3 times root 38. That's equal to the cosine of the angle between the vectors. To solve for the angle, we just take the inverse cosine, and since this is a pretty ugly number, we just plug it in the calculator to get some decimal and then press the inverse cosine button. That gives us around 1.46 radians, which is about 84 degrees. This operation leads us to another definition. We want to understand that if the angle between the two vectors is half pi radians, or 90 degrees, these vectors are orthogonal. This pretty much means the same thing as perpendicular to one another. And it's important thing to note that any two orthogonal vectors will always give a dot product of 0. Because the cosine of half pi is 0, this means that if we're computing a dot product and you get 0, those vectors are orthogonal. Now we are on to, now there is another way to multiply vectors other than dot product. Since the dot product is a scalar, there is another way to multiply two vectors and get another vector and a new vector and this new vector. This is called cross product. Cross product which donates to a multiplication sign. Now that's what we a little more about vectors. We are ready to understand and how to find out how to do cross products of two vectors. Let's learn how to do that now. Let's take two vectors a and b. A has components 1, 3, 4, which can be expressed as I plus 3j plus 4k, and b has a component 2, 7, negative 5, which can be expressed as I plus 7j minus 5k. The way you can find the cross product as the cross product or A cross B is by finding the determinant of the following three by matrix, which is I, J, and K across the top row. The component from vector A in the second row and the component from vector B in the third row. We all know to get the determinant from 3 by 3 matrices, so this is no problem. We just get I times the determinant of 2 by 2 matrices minus J times the determinant of this one plus K times the determinant of this one, and you can find each one of these determinants. First we have a negative 15 minus 28, the negative 5 minus 8, and the 7 minus 6. Simplifying and combining with the unit vectors, we are left with a negative 43i plus 13j plus k. So we can see how using the determinants we have found the cross product and of these two vectors, which is another different vector. We must understand that a vector cross product will always yield a vector that is orthogonal or perpendicular to the original two vectors, or rather to the plane containing them. In fact, if you place your edge of your hand directly on vector B, curl your fingers in the direction of the vector A so that your hand sort of mimicking the angle formed between them. Your thumb will be pointing in the direction of the cross product. In a different way, you can point your index finger in the direction of A and your middle finger in the direction of B, and again your thumb will be pointed in the direction of the cross product. So the right hand rule that we originally learned from the three-dimensional coordinate system can help us understand the directions of a cross product. First, if we take the cross product of a vector and itself, like A cross A, you will always get 0. This will be easy to prove to yourself if you work out the determinant just as we did before, and you can see all the terms cancel out each other. Also, we can make the following statement about the length of the cross product vector. The magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. The definition also can be used to find the cross product of two vectors, because the magnitude and the direction are the two pieces of information conveyed by any vectors. If we calculate the magnitude of the cross product this way and determines its direction by using the right hand rule, we can therefore accurately define the cross product. From this method we can also arrive at another truth, that any two parallel vectors must have a cross product equal to 0. That's because parallel vectors have an angle of 0 between them, and the sine of 0 is 0, so the whole cross product according to this expression must go to 0. One another interesting thing about cross product is that the magnitude of a resulting vector, which is AB sine theta expression we just used, is also can be equal to the area of a parallelogram created by vector A and B. This is another reason that cross product of a parallel vector is zero vector, because the span 0 area. Lastly, just as we learned some properties of dot product, let's quickly mention some property of cross product. First, the cross product is not damn. Cumulative. Damn. A cross B doesn't equal B cross A, rather A cross B equals negative B cross A. Second, the cross product isn't associative. The quantity cross A cross B cross C is not equal to A cross the quantity B cross C. However, the cross product doesn't distribute across that A cross the quantity B plus C is equal to A cross B plus A cross C. This understanding of the cross product will make sure for our purposes, and we will also know that the cross product crops up all the times in physics, but let's keep going with the linear. And thank you so much for listening to my video, and best of wishes, and I hope you understood. Got a little messed up in the tough words, it happens sometimes. Best wishes, and thank you for listening to my video recording. Best of luck.